for the last talk of the session, I'm going to hand this over to Qiyuan to tell us about automating separation logic.
Can I start now? So finally, the last talk in this great day, and I'm Qiyuan, and I'm so excited to present my our work about generically automating separation logic. So let's start. So we know it's very common that we use predicate to represent data structures in separation logic, and we also use abstract predicates to hide complexities from internal implementations. However, I would say actually complexities are just invisible, but not eliminated. Why? Because we know current reasoning mechanisms still have to unfold the predicate if necessary, and if you unfold, other hidden complexities come out, and your expression can explode. So that's why we say unfolding is bad and compositional reasoning is good. However, compositional reasoning also has its problem. So it considers predicates as sealed, as encapsulated, but it relies on the reasoning rules of the predicate to work, right? So the problem is, where do we get the reasoning rules of the predicate? Maybe we want users to provide them manually, but you know, people are lazy. So why not automatically generate them? So hey, look at our work. So, you know, it's ambitious, and the big challenge is data structures can be very various kinds, and how do we generically generate their reasoning rules? So we find the algebraic approach. So first, we identify fundamental algebraic properties about predicates. And second, we design some reasoning rule templates parameterized over the algebra axioms. And at last, we derive the properties of the predicates so that once we derive the properties, we can instantiate the templates and obtain the reasoning rules for the predicates. So let me introduce the overall scheme of our reasoning system. So let's begin with some separation logic reasoning tasks. First, we can reduce them to entailments between composite formulas, and then we reduce them to entailments between predicate applications. And this is where we want to apply some reasoning rules to deduce them or to solve those entailments. And those rules are instantiated from hard-coded templates together with algebraic properties stored in a database. And the database can grow later. And when we face some new predicates, we could derive their properties and to enrich this database and then enrich the power of the entire reasoning system. So finally, the outcome is some proof obligations in Isabelle Hall, and we could send them to SMT servers or Sledgehammer. So before I introduce the technical, theoretical details, let me set up some preliminary. So all our findings are based on a truth that separation logic predicates imply data refinement relations. So I have an example here. For example, a predicate about an array at address, and of value L, and this implies the refinement where the refinement relation is array parameterized by its address, and the abstract object is L, and this L is kind of the algebraic some abstract list provided by the underlying proof assistant, and the concrete object is the memory heaps. So here, the entailment between predicate applications, it implies transformations of abstraction from one refinement relation to another. So for example, here, it implies that the transformation from a single reference to the refinement of an array and its abstraction changes from the V to a singleton list containing the V, the element only. So now there's a problem. Look at this predicate. It has two parameters. So which one should be considered as the parameter of the refinement relation, and which one should be the abstract object? So to address this, to answer this, we introduce an explicit notation, a type-like notation. So the value, so the left side of this type column denotes abstraction, and everything at the right-hand side is about the refinement relation. And we also introduce diagram arrow-like notation to represent the transformation. So here F is a partial map, and it represents a transformation from the domain of this partial map of type T to Fx of type U. So for example, the previous entailment can be written like this. So now this provides us an inspiration. So it really looks like some type notation in a type system, right? But you know, in a type system, the array is usually parametric. So it looks like this. There should be some parameter T that represents, so here represents the refinement of the elements. So could we have some parametric type like this? Sure, we can have higher order predicates, right? So it's array the higher order one from the predicate to another predicate. And also, you know, the transformation is the core of our reasoner. So could we have some subtyping rule that transforms the element refinement of an array, for example, here to transform the T? And here, let me show an example. For example, we have a transformation from a pair of integers to rationals. And its morphism just transforms the representation of its abstraction. So here from a pair of n and d to a fractional. And then maybe we want, it's very natural that we want some transformation from an array of pairs of integers to an array of rationals, right? And its morphism is just the original morphism wrapped by the mapper operator of the list. So just this map the lambda nd like this. So naturally, you could generalize this for any container, right? So this F, for any F that represents any container you want, like a list, like hash map, hash set. And then we could, so this is the first property found in our work about transformation functor, and it allows you to actually change the refinement relation of the element of any data container. So here is the problem, actually. So you may notice here our separation logic not only specify memory heaps, but also any concrete objects. For example, here the transformation above the line, so a pair of integers. And this actually allows us to use separation logic to specify any every layers of stuff in program, maybe down to the entire program state that about memories and maybe file storage and maybe others, and maybe up to a single atomic value. And this functor property allows us to reduce the reasoning problem about the containers to a problem about their elements. So it allows us to, for example, once we have a transformation problem about program state, we could reduce it to a smaller problem about data structures in memories. And if the data structure in an array, we can reduce it to an even smaller problem about elements of array, and if elements is the record, the fields of about this record, and finally we reduce the problem into a single atomic problem about a single atomic value. So the key here is we could use separation logic to specify every layer of programs. And we could use one automation mechanism to automate all of this using this functor property. So, okay, this is our first finding. But this finding is about, maybe I could say about a hierarchical dimension. So could we have some property or some automation for the component-wise dimension for example, so this red arrows between components. So let me give an example. So for example, we want to transform a slice to another slice. Let me first explain the notation here. So first, a slice is simply a segment of an array, and the parameter of the slice, for example, here the A and the B are intervals that represent the domain of slices. And we use addition, so here A plus B, to represent interval concatenation, actually concatenating two adjacent intervals. So here the A plus B is a concatenating of the two intervals. And then return to our problem. So here we want to transform a slice of domain A concatenated with B into another slice has a domain B concatenated with C, and we find the domains doesn't match. So this transformation is not trivial. So how could we do this? Maybe we first move the target slice slightly to align the common part B, and we can see actually this transformation will leave some given part, some A remaining, and this transformation also requires some part C to be given. And this is quite a standard situation for bi-abduction. And the remaining part is called frame, and the missing part is called anti-frame. So the answer for this transformation is just instantiate the frame to the slice of A and the anti-frame to the slice of C. So here, we first cut the given slice to two parts, one for A and one for B, and leave the A remaining, and then we get the anti-frame, the missing part C from just assume from the subsequent reasoning process. Anyway, we get the part C, and we concatenate B and C into the final target. So here, let us formalize the key properties used in this procedure. So we write, it's just the cut and the concatenation part right here. So transformation from a slice of A and B to two parts and later merge them back. So we could also have a very natural generalization to use this F to represent the slice of any data structures. For example, the slice of hashing maps. And in this case, the A and B could represent the domain of the sub-hash maps. So there's a problem. Why do we call it distributivity? Because it really corresponds to a semi-module in a semi-module. And in normal notation, a semi-module contains three parts: a partial semi-ring, a commutative monoid, and the scalar multiplication. And in these settings, the partial semi-ring is the domain of the slices, and the commutative monoid is the separation logic predicate, the set of all predicates, and the monoid operator is the separating conjunction. And finally, the scalar multiplication is the F, so the slice operator itself. So maybe limited by time, maybe I will be slightly quickly. So let's just skip this example about the linked list segment, but you could refer to our paper. So finally, let's return to the content of our talk. We have identified some properties, and we also skipped the reasoning rule templates because it's very technical and somehow boring. So let's go to the final part about how to derive the properties of the predicates compositionally. So when we say compositionally, we mean predicates are built compositionally. For example, here a target predicate T is defined based on many other predicates like U1 and U2 to U4. So we want to derive the property of target T without unfolding the components of T, so unfolding the U1, U4. So how do we do this? Let's see what we have now. We have an entailment reasoner based on some algebraic properties, and we want to derive the target property. So first, we unfold the target property, and we need to show some transformations, and then we unfold the target predicate or apply induction if the predicate is defined recursively. And now our goal reduced to separation logic entailments about the components predicate. And then everything we need to do is just send the entailments to our entailment reasoner. And this reasoner could apply the known properties of the components predicates to show the target to deduce the target entailments, and finally give us proof obligations that entails the correctness of the property. So, okay, this is basically our work, and I will show you some experiments of our work. So, the first column gives some interesting cases, and the second column is a manual rule that have to be manually crafted in this case. So you can say most of the cases can be fully automated, and you don't need to manually provide any rule. And the third rows are the total annotations in the radio to the total line of the source code. And this column gives the annotations that used to folding and unfolding predicates. So you may have a question. So we already said that unfolding is bad, but why do we still need some unfolding here? Because just that we still need unfolding to reveal internal data representations. For example, if you are going to verify dynamic array, you really need to unfold the abstraction to reveal its internal buffers and others like this. So I mean, here the unfolding is something still necessary. And finally, the other column represents the annotations that accepts all the folding notation and the looping invariants. And so the other notation represents maybe the actual, some really hard annotations need to do. So basically, we can realize some very good performance, good automation. And the overhead column gives the total lines of the proof code annotations and also specifications for properties. So, and finally, the LOC to represent the line of code, and the time is the total time used. The first column of the time is the time for reasoning, and the second column is for sledgehammering, and the last one is for evaluating the proof obtained by the sledgehammering. So, okay, this is basically the talk of our work today, and I introduced the functor distributivity, and it's said that there are other properties not present today. So basically, the separating homomorphism is a functor functor property in the setting of bioproduction, and for other properties, you could find them in our paper. So, okay, I think this is a major topic of our work. Yeah. Thank you.
Questions?
Just a quick experimental question here, because you listed some examples, like 150 lines of code that could take up to like 6 to 9 minutes to get analyzed. Is this for single thread or single CPU? Like, what exactly is the setting?
Okay, so the longest time about 10 minutes, and we use i9 CPU, basically the best CPU you can find now.
Yeah. It still took like almost 10 minutes.
I mean, the most time is taken by sledgehammering. So the first column, the reasoning time is still efficient timing.
Thanks.
Hi, thank you for your talk. So if I understood your talk properly, you want to have algebraic properties for the predicates so you don't have to unfold them as part of reasoning. You still need to unfold them to prove that the invariants hold in the implementation. So I wanted to ask, in these experiments, how much of the code was client code that relied on the algebraic structure?
Well, maybe it's hard to say the exact portion of the code, but actually, at least for every step of reasoning about the fields and to access the fields, we require the functor properties. And in the case for quicksort and the stretch matrix algorithm, we require the slice property, the distributivity property to cut and concatenate slice.
Okay, thank you.
15 seconds left. You have a short question?
Oh, I thought I only have 5 minutes when you show me this.
Not including
some
questions.
time for question, maybe. Yeah. Sorry.
Okay,
maybe.
so sounds like we should thank the speaker again.